Chapter 9, Global Atmospheric Change. So this chapter deals with probably our biggest challenge from an environmental standpoint, and that deals with issues related to climate change. We used to refer to it as global warming, but again, I think it's probably a more appropriate term to use climate change, because it's not necessarily the case that everywhere on the planet's going to get warmer if the climate change continues. So, with that said, some of the biggest concerns that scientists have relate to the melting ice caps and how that will definitely result in rising sea levels, and then how much of a concern we have with that with respect to all the things that might alter. It's definitely documented that both the continental and polar ice cap is melting. Around the world, in general, glacial ice has continued to diminish by about 46 feet from between 1955 and 2005, so just in 50 years. Again, I know most of us don't really have a reference as to whether that's a lot or a little, but it's definitely a lot. There are images in the book that show Muir Glacier in Alaska in 1903, and then again in 2004, and again it's pretty stark visual evidence how dramatically that glacier has shrunk over that amount of time. Again, I'm still somewhat surprised that there are so many people that don't believe that we are having an impact on climate change. Again, we'll get into a lot of the details in this chapter. It's not that nature doesn't cycle. It's not that we haven't been warmer or colder than we are now. It's really what's worrying is the rate at which these changes are happening, how quickly these changes are happening. And there's clear evidence that it's CO2 emissions from us burning fossil fuels that would otherwise be stored long-term under the surface of the earth. So us being the anthropogenic sources of the CO2 that we're burning, that's definitely a major contributor, throwing the carbon cycle out of balance. So to understand this issue, we have to make sure we really understand the relationship between the atmosphere and our climate. A couple words that people oftentimes use interchangeably are weather and climate. Keep in mind that weather are conditions in the atmosphere at a given place and a given time, and that these conditions can vary hour to hour. So the weather today might be partly cloudy and a light breeze, and it might be 59 degrees and 35% humidity. That's the weather. But the larger scale weather patterns that occur over periods of years actually is what our climate is. And largely this is determined by the distance that the earth is from the sun, how water and land are distributed across the surface of the earth, the type and amount of vegetation that's in a given area, along with primary factors like temperature and precipitation. So again, climate changes over long periods of time, and we've documented that throughout the history of the earth. There are places that are moist forests now that were maybe deserts in the past, and the other way around as well. And of course, everything that lives in the climate that it lives in, it's there because it's adapted to that climate over, again, long periods of time. As I mentioned, the big challenge is when the climate changes so rapidly that living things in that climate maybe aren't able to adapt to it quick enough. And again, we'll chat a little more about that. So as we've already talked about, the earth is warmed by the sun, and our atmosphere, with all the things we just spoke about in the last chapter, basically make life on this earth possible. Without the sun's energy, the plants on this planet, the photosynthetic organisms, would not be able to harness the sun's energy and convert it into another form of energy that we and other animals could utilize directly. About 70% of the sun's solar energy is absorbed and used to run the biogeochemical cycles that we spoke about earlier, in addition to keeping the planet warm enough to support life and, again, to power photosynthesis. The image on the right basically shows a solar radiation budget, with the solar radiation entering the atmosphere. About 49% of it's absorbed by the land and the oceans that heat up the earth. And then you can see the relative proportions of that energy that's re-radiated back. Some of it is absorbed by clouds or absorbed by the gases and other things that are in our atmosphere. And that leads to that 69% number, the total absorption by our atmosphere, land, and water. And then some of that is also reflected back to space, again, about 31%. So that accounts for the 100% total. It's really a very delicate balance that allows for life to exist on this planet. And if we add more stuff to the atmosphere, particularly things like CO2, it actually changes that 69 to 31% ratio. If more of that solar energy is maintained in our atmosphere, then it relates to higher temperatures. So we'll look at some more of these things in detail. We know that the whole Earth is not equally heated by the sun. More solar energy that hits directly in places like the equator results in a more consistent climate. So again, the image on the right kind of demonstrates that if the light is striking vertically like it does at the equator on the Earth, then basically you get a smaller area of illumination, which means more of the sun's energy is directed at the surface of the Earth, which makes it warmer. As you move towards the north or south poles of the Earth, the light is spread out over more surface area, so it doesn't have as great an impact on warming. So again, just a good illustration on the right there of why the equator is warmer versus why the poles are cooler in general. So again, basically as we move up and down in latitude from the equator, we get cooler. We have shorter seasons, we have longer seasons and shorter seasons, and so those factors basically drive the climate of an area, and then ultimately that climate drives what type of living things can be there. On top of the angle that the sun is striking the Earth, keep in mind also that the Earth is tilted on its axis, so the Earth doesn't kind of orient itself straight up and down relative to the sun. It's tilted at about 23.5 degrees perpendicular to the orbital plane that the Earth travels around the sun on. And so basically it's this tilt that determines the seasons. So where we are in the northern hemisphere, as the Earth is going around the sun over the course of a year, when we're tilted towards the sun, so when the North Pole is tilted more towards the sun, that basically is our warm time of the year, roughly between March and September. And then as the Earth continues to rotate around the sun, when the North Pole, in the northern hemisphere in other words, is tipped away from the sun, then that is our winter. So again, this relates back to the previous slides where we were talking about the angle that the sun's energy is hitting the Earth. If the Earth is tilted in the northern hemisphere towards the sun, then more of the sun's energy is directed in a smaller spot, which is why we have summer. When it's tilted away from the sun, the sun's energy is spread out more, so that's, again, why we have winter. Back in an earlier chapter when we were talking about biomes, we talked about temperature and precipitation being the primary factors that determine what type of biome exists. So precipitation clearly has a huge impact on climate then, and again, climate determines biomes. So precipitation is any water that falls from the atmosphere, whether it's liquid or a solid like snow or hail. And again, precipitation doesn't equally fall to the earth in equal amounts everywhere. That's why we have rainforests that get more than 100 inches a year, and we have very dry deserts that might not even get an inch a year. So the reason that there's such a differential on how much precipitation hits the earth is largely because of factors that include how much moisture is actually in the atmosphere. And we go back to looking at how the winds flow differently around the earth. So we get that uplift of warm, moist air near the equator. And so how much moisture is actually in the atmosphere is going to obviously dictate then how much there is that's available to fall back to the earth. Geographic location plays a huge factor as well. Whether you're on the center of a continent versus near the ocean, those kinds of factors, as well as topographic features. In California, we have some great examples of how our mountain systems dramatically affect what areas in the state get more rain and less rain. So we have a lot of examples of rain shadow effects in California. We have it on the coastal mountains, where the ocean side or the western slope of the coastal mountains are much moister. They have plants that tend to thrive in more moist environments. And then as you go up and over those coastal mountains, then you start getting the rain shadow effect. All the moisture has already been kind of wrung out of the clouds. The warm air near the ocean can hold more moisture. As those clouds are pushed up in elevation, they get colder, which causes the moisture to be wrung out of them. And then when that system passes over the mountain, it's going to be drier. It doesn't mean that it won't rain at all, that it has no moisture left, but it's going to be much drier than it was. And so then we have the same effect in the Sierra Nevada. Much moisture on the western slope of the Sierra Nevada, and then we have our deserts and much drier climates on the eastern slope of the Sierra Nevada. So again, differences in precipitation, which are affected by the amount of water in the atmosphere, the geographic location you're in, as well as topographic features like mountains, all have a huge impact. The rain shadow effect is discussed a little more in the What a Scientist Sees section. And again, we basically just kind of walked through that, so reread that. But again, the bottom line is that warmer air can hold more moisture. So as warmer air is forced up over mountains, which again, as we go up in elevation, we get colder, the rain is forced out of the clouds, and then as those air masses continue up over the peaks of the mountains and down the other side, they're much, much drier than they were. The systems are much drier and therefore have less moisture that can actually fall out, creating a more arid region on that side of the mountain. So now on to some of the specifics about climate change. We know for a fact, based on measurements, data that we've been collecting for quite some time, that the Earth's average temperature has been increasing, as indicated by the figure on the right. The average near 14 degrees Celsius back in 1960, up to around 14.6 degrees as of 2010. This is based on a lot of different data. These are typical measurements that are taken every day around the world at meteorological stations. The Channel 7, Channel 12 news out of Redding and Chico keep measurements every day of temperature and basic weather conditions. So we've got all that data plus the different government agencies that collect data, setting up weather balloons to monitor the upper atmosphere. Scientists even that we have here in Redding at the Forest Service office that are looking at tree rings, looking back maybe hundreds and even sometimes thousands of years on very, very old trees and looking at the growth rings. Close growth rings typically mean not very much growth, and typically that's fairly closely related to the amount of moisture or precipitation that we get on a given year. So we can use what's called dendrochronology, basically looking at growth patterns of trees, and that can give us a lot of data going back before we were ever collecting that data. The National Oceanic and Atmospheric Administration has indicated that global temperatures in 1998 and then 2001 to 2010 were the hottest years on records. The last 2 decades of the 20th century were its warmest, so the 80s and 90s were warmer than any of the previous decades in that 20th century. There have been more heat waves, more heat-related deaths because of those heat waves. People who live in areas that typically don't constantly get as warm, and so therefore they're not typically prepared for that kind of weather that happens, those temperatures that get way hotter than that are typical. And so again, people aren't prepared for that, they're not used to it, and that's why we've had more deaths. And then of course the noticeably rising sea levels, glaciers in many places around the world, up in the mountains, as well as the far north and far south part of the earth, retreating, getting smaller, more severe hurricanes. Again, there's always you have to be careful in balancing this. You'll sometimes hear on TV that, this was the worst hurricane season we've had on record. That statement almost makes it sound like, in the past million years, we haven't had hurricanes that bad. Well, again, how long have we been keeping specific hurricane records? 100 years or so. So, again, the trends are dramatic and are occurring very rapidly, and that's kind of the take-home message that we really have to be concerned about. Again, there's no doubt that our planet has, on average, been warmer than it is now, as it has been colder than it is now. But we're seeing these alarming trends that are happening in very short periods of time compared to the hundreds, if not thousands of years that these kinds of things happened in the past before there were this many of us on the planet. Spring in the northern hemisphere has been coming about 6 days earlier than, say, about 50 years ago, and autumn is coming about 5 days later. Again, these don't seem like very large changes to us. But when you've, again, got plants and animals that are adapted to the climate, those slight changes really affect their phenology. So the cues that tell a plant when to start leafing out or when to start, producing flowers. I was just noticing it's more of a function of just, this year being so dry and so warm. But up where I live, for the last probably 2 weeks ago, if not maybe 3, there are manzanita up here that are already flowering. And normally, on average, those manzanita bushes wouldn't start making flowers until probably at least April. Maybe March, but April. And so again, this is one little short-term thing that may not have anything to do with long-term climate change. And one of the things that kind of frustrates me when I hear people talking or when I see things in the news, they point to one event. We had one worse than average hurricane season, or we had one 80-degree day in December or January. And it's like, see, this is proof of climate change. This is proof that the planet's getting warmer. Again, even though I agree absolutely that we are affecting the climate, people make the mistake of claiming one little point in time as being indicative of something in the bigger picture. So again, just be aware that the data out there is supportive of our changing climate and more rapidly than normal. But again, those individual little one-time events that may be showing a bigger trend just aren't by themselves evidence of anything. In past decades, we've seen the sea levels rise as glaciers have retreated and as hurricanes have become more severe. All these things, again, together are trends that have been showing a negative trend that's getting worse and worse and worse over time. Again, these changes are pretty clearly demonstrated because of more carbon dioxide. The figure on the right shows the level of carbon dioxide concentration in the atmosphere going back to 1958. And you can see the seasonal fluctuations, high in the winter, lower in the summer, and then the solid line that shows the annual average. Again, the main thing to focus here is the trend. The trend is consistently going up from 315 or so parts per million up to getting very near 400 parts per million. Again, we know this is measurable. We know where it's coming from. It's largely coming from us at a greater rate than would normally have happened. The United Nations charged the IPCC to conduct a scientific assessment of climate change. This was done by a group of scientists who had no stake in the results. No company was paying for this research. The scientists were just in it to see what the data said. And from the analysis of their data, they are predicting anywhere between a almost 2 degree and a 4 degree increase in global temperature, among other factors. Again, that's a huge change in an average global temperature that is substantial enough that it could substantially affect the plants that live in given areas. Some areas may get too hot and dry for a certain type of plant to survive, which then means there may be animals that can't survive in that climate either. There may be other climates that get colder or have too much moisture for certain types of plants to continue living in that area. So some of these plants might go extinct. Some of the animals that are associated with those plants might be affected negatively. Some might be able to move, the animals, of course, not the plants. But not all of them will be able to adapt quick enough to the change. And again, that's the key thing I want to say one more time. It's not that the change is happening. It's how quickly the change is happening that's really the problem. So these anthropogenic accumulations of primarily CO2, but also methane, various nitrogen oxides, the chlorinated fluorocarbons, ozone, have all been adding to the effect of climate change. CO2 again is the primary factor that's increased pretty substantially over the past 200 years. And again, we know where this comes from. It comes from primarily 70% of it from burning fossil fuels. Keep in mind that the fossil fuels that we dig out of the ground or pump out of the ground have been there for millions and millions and millions of years, and basically are a long-term way to store carbon dioxide in what were once living things. So the fossil fuels like petroleum that are miles below the surface of the earth would never have been able to just make it to the surface of the earth in large amounts on their own. So again, it's definitely us digging it out of the ground and burning it. And again, the key thing is burning it, releasing the CO2. And primarily, again, it goes back to cars, automobiles, releasing the nitrogen oxides and some of the carbon oxides. And so we know that once these gases get up into the atmosphere, they absorb more of the infrared radiation, in other words, heat, as it tries to go back out into space to keep the Earth at a good balance. And so again, this is the enhanced greenhouse effect. Greenhouses stay warmer inside because the sun's energy is strong enough to push through the glass of the greenhouse, but then it's not strong enough to go back through the glass out into the atmosphere. So there's a net increase of heat that occurs. And again, that's what's going on with the Earth on the bigger scale. Sunlight's being absorbed by the surface, and then as it's being redirected back out into space, It's bouncing off the clouds, it's being reabsorbed by the atmosphere, all the CO2 and the nitrogen oxides, and so it's being trapped down near the surface of the earth where we live. So this radiative forcing is the capacity of the earth to retain heat. Again, that's completely necessary for life on this planet. The problem is when things get out of balance and more of that heat is retained and doesn't escape out into the higher levels of the atmosphere. Again, this isn't anything new. Natural forces can affect the atmosphere's ability to retain heat as well. We've already talked about volcanic eruptions and the types of pollutants they release, the particulate matter. When we've had volcanic eruptions in the past and those particulates have been suspended in the atmosphere, they've resulted in changes to our climate, especially very large volcanic eruptions. They can stay up in the atmosphere for days or months, and those types of factors, particulates in the atmosphere, tend to cool the atmosphere because they actually block the sun from getting down to the surface of the earth. So we've had times in the past when that has, to some degree or another, affected the climate on the earth. And then we add to that human-induced aerosols, sulfur emissions from burning coal. Those things then compound to have the opposite effect of the warming impact. They tend to make the climate cooler. Again, all of those things have been in force on this planet since the Earth was created. So the ozone up in the stratosphere that, again, allows life on this planet to exist, and the aerosols that get into the atmosphere cause the atmosphere to hold less energy while causing other gases to hold more energy. Again, it's the humans and what we're doing that are causing a net increase in the radiative forcing of the atmosphere because of our combustion of fossil fuels. So again, what are the effects of global climate change? Well, we definitely know that some areas that were and that are primarily covered in ice are melting, as well as some of the ocean areas that have a covering of ice over them relatively permanently are decreasing. Our ice caps at the North Pole have decreased especially rapidly in the past several decades. The more of that solid water that's released back into liquid form, the more our sea levels are going to continue to rise. Again, water expands as it warms up, so that increases then the overall depth of the ocean. The weather patterns are being impacted by the changing climates. Therefore, again, some areas might get less precipitation, other areas might get more precipitation. There's some serious concern that some of the major forces that are driven by the difference between the cold air at the poles and the warmer air near the equator that we've already looked at are getting or can get so disrupted by this warming trend that it could even affect ocean currents that might not flow the way they have. And again, then how much of an impact might that have on the ocean life? Things that we are so large scale that it's hard for us to even predict. Then you think about just the impact that rising ocean levels alone could have on humans, on agriculture. Awful lot of people around the world live near the ocean because of all the resources it provides for us. You've got millions and millions of people in some countries that live very near the ocean. A few feet of land that's, or a few feet higher of the ocean could result in hundreds of feet of land being covered by the ocean. And again, that could affect the amount of land we have to produce food, but it also could clearly affect the amount of land we have to live on. It's one thing to have the technology, maybe just to raise your house up a little higher or whatever, but you think about most of the people in the world that live in these areas that are near the ocean, and if that ocean level rises, where are they going to go? They may not physically be able to move anywhere else. Or if you have to relocate these people, then you're just creating an even denser population of people, concentrating them into even less land. There are island nations that could conceivably be completely underwater if the ocean levels rise like we predict they might. The Maldives are one example where those islands could be completely underwater. And then where do those people go, and how much is that going to cost? There's another really big impact that's potential in areas that get warmer and maybe even moister than they used to be. Diseases, insect problems are better, or I should say they're more of a problem in areas that are moister and warmer. Those kinds of climates cause perfect conditions for mosquitoes, for example, and we know all the different diseases that mosquitoes can carry, things like malaria, West Nile virus, a bunch of other problems that affect people worldwide. So again, in those areas that get warmer and maybe even moister, now we might have new disease outbreaks that we're going to have to address. Some of the mathematical models that scientists are looking at predict that just within perhaps the next 6 or 7 years, the North Pole might not have any ice during its summer. Again, in our recorded history, that's never been the case. The ice pack shrinks in the summer and grows back in the winter, but there's always been a core of ice there. And again, these models, at least the aggressive ones, are showing that could be totally disrupted within just less than a decade. The figure on the right basically shows the ice volume, and if we look from 1979 to current day, again, you can see the trend is a decreasing trend, up and down seasonally, higher in the winter, lower in the summer. But again, you can see the trend of that data is still downward. So by gathering as much data as possible, running computer simulations, those are the kinds of things that we do to give us predictions about the future. And again, in this case, the predictions are not great. As I mentioned, there already are indications that there have been more deaths because of heat-related illnesses. As I mentioned, mosquitoes can expand their range. Populations can dramatically increase if the conditions are better for them. And then again, there's a whole suite of diseases that could become more problematic. Now, again, in most cases, the developed countries have vaccines and have the ability to treat people that get these diseases. Where the biggest challenge is going to be is in those developing countries where they don't have the basic medical care and children don't typically get immunizations. In 1998, there were surges of cholera in many developing countries, countries that typically have diseases like cholera present, and yet the conditions are starting to favor even greater outbreaks of these diseases. We also have a lot of measurable changes that we've been able to identify in plant and animal species in relation to their biology and how they're dealing with or adapting or being affected by changes in climates. Just a couple examples. With the Antarctic temperatures getting warmer, therefore the oceans getting warmer, the penguins' food supply is reducing, and therefore if the penguins aren't as healthy because they're not getting adequate nutrition, their reproductive rate's going to suffer. I was just talking to my wildlife class about the gray whale. We have populations of the biggest mammal on the planet, the gray whale, that kind of migrate up and down the California coast to reach their breeding grounds in the Baja Peninsula. I forget the exact year, but fairly recently there was a lot of dieback, a lot of dead gray whales washed up on the shorelines, and the scientists noticed that they were emaciated looking. They just looked like they weren't getting enough food. They live on basically microscopic living things. And if the water temperatures are warming up, making the plankton's habitat no longer suitable for them, or at least no longer suitable to produce as much as it used to, then again it has the impact potentially to affect everything in the food chain. The coqui tree frog in Puerto Rico has become rare due to climate change, ocean warming, along with, again, the chemicals that we've been dumping in the environment, causing air and water pollution. The acid precipitation has worldwide been having an impact on coral, literally bleaching it out like the image you see on the right. That white coral is not supposed to be white. It's supposed to be colorful. But the temperatures get too warm, and again, all the other stresses that are directly related to us then have that negative impact. And if the coral starts dying off, then all the other living things that depend on the coral reefs start dying off. And ultimately, those are resources that we depend on. We don't eat coral, of course, but we depend on a lot of ocean species for food. Sometimes countries like ours maybe don't depend on it as much as other countries. But again, all of these little pieces of the puzzle keep getting affected. And pretty soon, it will no longer have the ability to support the type of life or the quantity of life that it used to. So basically, there are two ways we can deal with climate change. We can mitigate the effects of climate change, which is moderating them by reducing greenhouse gases. Given time, given the reduction in greenhouse gases, we could start to reverse some of those trends. But it won't happen immediately. If we stopped burning as many fossil fuels today as we used to, the climate would start going back into a balance, but it could take decades or hundreds of years. Again, that's not likely. We're just going to stop burning fossil fuels tomorrow. So we have to continue to find ways to mitigate the effects by using electric vehicles, but again, not charging those electric vehicles by plugging them into fossil fuel power plants, by using other alternative sources of energy, and probably things that we haven't even thought of yet that we'll find in the future. Again, the hope is that we don't do so much damage before we find a solution that we can't undo the damage. So the real focus is, and will have to remain, on reducing carbon dioxide emissions. So again, that's something that we directly have control over. By not burning fossil fuels as much as we do, not depending on them for so much, that by default then will release less CO2 into the atmosphere, which again, hopefully then we can get back into a better balance, get the CO2 cycle, carbon cycle, back into a better balance, where more of that CO2 is stored and less of it then is back up in the atmosphere, creating the greenhouse effect. So ultimately, the goal that we have is to continue to develop alternatives to fossil fuel. In other words, using more renewable energy. Along with that, though, we have to continue to look at reducing energy use and increasing the efficiency of the machines that we do use. Automobiles have continued to get more efficient, and not just the obvious thing like gas mileage. I mean, that's part of it. Getting better mileage means the fuel that you're burning is being burnt more efficiently. But again, that's one big piece of the puzzle, but that's just one piece of the puzzle. Carbon management is a whole separate issue, which basically is in general how we need to pursue separating and capturing the CO2 that's produced when we're burning fossil fuels. Right now, it pretty much just leaves the tailpipe or leaves the smokestack. Some things may be scrubbed or cleaned out, but largely that emission then just goes right out into the atmosphere. We have technologies that work to do this, to manage our carbon output, but again, a lot of them are very expensive and not practical at this point. But we've come a long way in automobiles. I know there are a lot of car lovers out there, including me, who kind of look back at the days when an automobile engine looked like an engine. You could still work on it because you could identify everything. Now you look under the hood of a car and there's so much electronics, so many things going on that are related to emissions controls. And again, that's a good thing. But it's just a different, we have to get used to this now. This is the way it is. And again, it's definitely a good thing that we're taking as many of these emissions out of the combustion process as we can. But again, we still have a long way to go because we've had higher emission standards for decades. And as we saw in that previous chart, the CO2 levels are still increasing. I don't know when we're going to reach the limit of technology just focusing on automobiles, how much more we're going to continue to be able to get CO2 out of a internal combustion engine, which is why, again, we have to focus on not using internal combustion engines. We have to focus on using other technologies like hydrogen cells and, again, electricity that doesn't use fossil fuels to charge it up. Again, the other part of this is adaptation. How do we adapt to climate change? Most people believe that the most pressing issue is the rising sea level. And so then the simple solution is just to move people who live near the coast inland. Again, that's simple in theory, but where do we move those people to? If there were other suitable land, they might already be there. We can use technology, which we do already use, to perhaps construct seawalls on coastal areas that would, even though the city on the coast may be below sea level, the seawall would keep the ocean out. Again, that works great like it did in New Orleans until you get a major hurricane that comes through and breaks the wall down and floods the city and results in death. And of course, it's super expensive. While we might have the money and the technology, again, to do that in developed countries like the U.S., where are the countries going to get the money to do this in other places and in the poorer countries? Water could be channeled to prevent the saltwater intrusion into ag lands. If the sea levels rise, the salt water is going to creep upriver more than it does now. And the farther that salt water creeps up into the freshwater, the less water there is for us to use for agriculture and for drinking. So again, we might have to alter river systems, at least as they approach the ocean, to keep that seawater from getting up into the freshwater. And then when you think about it, there's no way to avoid that underground, the groundwater that would get saltwater intrusion. There's no way to stop movement underground of saltwater into freshwater. As climates change, whether they get warmer or cooler or wetter or drier, some of the crops that we're growing in places now may no longer be able to tolerate the changing conditions. So we're going to have to continually find different crops that we can grow that are more adapted to drier, warmer areas, or that can resist diseases if they're growing in cooler climates. But there's even, again, another challenge to this. If you think about the middle of the U.S., kind of what we call the breadbasket, where we grow so much corn and wheat, staple food products. If those areas get, say, too warm and too dry to keep growing those kinds of crops, well, why don't we just grow them farther north? We could grow them up into the Dakotas and Canada, because that would be, say, a climate that is similar. If it gets too hot to the south, it probably means it'll get better to the north. So in other words, a climate to the north that was too cold before to grow certain types of crops, because of climate change, global warming might be just the perfect climate. Well, that's one little piece of the puzzle. Just because a climate gets warmer doesn't necessarily mean, and it doesn't really mean at all, that it's really going to be suitable for growing crops. We've got really rich, great soil in the grasslands throughout the mid part of the country. So it's the combination of climate and really good soil that allows us to grow so much food there. I don't know if any of you have been to the Dakotas or that southern part of Canada, but even if the climate gets warmer there, and let's say we even get more rainfall, that soil is not good soil for growing a lot of food items on. Up in Canada, it's conifer forests, so kind of acidic soil, may not be that thick, definitely not as nutrient rich as the soil to the south. So just because the climate gets better doesn't mean that we're still actually going to be able to grow food in those climates. Again, we can continue to engineer crops that'll grow better in dry climates or can stand some salt water, but we still got to have soil to grow those plants in. And then, of course, again, the developed countries are going to have to continue doing a much better job of harvesting all of the rainfall they can, building better storm runoff systems that are able to channel that water away, but also not just let it dump right back out into the ocean, capture it, clean it, and then use it for sewage, use it for drinking water. Again, every one of these things are not going to come cheap. If taxes are bad enough now, just imagine how much more taxes are going to have to be collected to pay for these sorts of broad scale things. We're not just talking about upgrading a city or changing something on a small scale. We're talking about nationwide having to make substantial changes. And again, that money is going to have to come from somewhere. So, if that wasn't depressing enough, and by all means, I think we have the technology and the common sense to just, to continue making progress and not let climate change continue to the level where it's going to destroy our ability to live on this planet. But I also worry a little bit that there are a lot of people out there that just don't believe that we measly little humans can have a big enough impact to change the earth. That's what really scares me, because I know that we are and can and have and will have a big impact on this planet. Hopefully, again, we switch technologies before it gets so bad that we can't recover from it. One of the other big problems that we face is ozone depletion up in the stratosphere. Again, up in the stratosphere, ozone is a natural part of the environment, and it's what makes life down here possible. But when we create ozone by burning fossil fuels and such, it is a very serious air pollutant. So we have the problem that in places on the planet, particularly the polar region, the North Pole, the ozone layer is being thinned. And again, we call this the ozone hole, where the levels of ozone up in the stratosphere are dropping dramatically. Again, we can look at imagery that shows the hole in the ozone layer grows and shrinks over time. And again, that's normal. But once again, the challenge is that it's growing bigger and shrinking less over time in recent decades. This despite the fact that we found specific things that were causing ozone depletion. The propellants that were used in spray paint and hairspray, we've done away with those. And that in theory should and did help. But there are other factors as well that continue to create problems. And again, it's not just a problem in our country. Other less developed countries are still using some of those cheaper technologies, which are those propellants that still do contribute to ozone depletion. those chemicals I'm referring to, again, are the chlorinated fluorocarbons. We discovered back in the 70s that they were one of the primary reasons for the ozone depletion in the stratosphere. And they were banned about 8 years later. And we also found other chemicals, halons, the nitrous oxide, chloroform, chemicals that are or were found in a lot of other products, also contributed to this. And so again, we in this country and developed countries have had those chemicals banned for quite some time. Yet we still find that ozone layer has continued to trend towards getting thinner and thinner. Again, a pretty simple little image here, but basically showing the effects of a thinner ozone layer. More of that UV light is getting through the ozone layer and making it down to the surface of the Earth. And we'll talk about some of the problems that causes. So if we have less ozone and we have more UV radiation, as I mentioned a while ago, is basically a type of radiation that can kill living cells. And so it can totally disrupt ecosystems just with higher levels of UV than we're supposed to get. Higher levels of UV radiation can affect vision, not only in humans, but probably anything with eyes. So, creating cataracts and other vision problems, creating weakened immune systems. And again, if you're already compromised, your immune system is already compromised in some way, then the higher levels of UV can further put you at risk for diseases. And then probably one of the biggest ones is just the higher incidence of skin cancer, melanomas. The graph on the right shows the average yearly ozone column over New Zealand and the correlation with the annual melanoma rate. Again, notice that when the ozone concentration dropped, how the trend of melanoma kind of kept going up. And then even once the ozone layer kind of thickened up again a little bit or got thicker, then that rate kind of still stayed pretty high. Again, in countries like the US, where we've got a pretty good healthcare system, you discover that early, it's treatable. You've got the problem, though, again, in those billions of people in those less developed countries that are even probably more likely to be exposed to it because they're outside more, working, farming. They're not protecting themselves. They don't have sun lotion. They don't wear sunglasses like we do. So you have this increased rate of health problems that are going to make them sort of less able to continue on with their lifestyle. And it creates, again, more of that downward spiral where worsening health means they can support less. Because they support less, the country can't thrive. And because the country can't thrive, the whole system starts becoming, problematic. So we are continuing to study this problem, and the more that we understand the intricacies of the problem, the more that we're going to be able to understand how acid deposition and climate change and ozone depletion all affect each other. There have been studies in lakes throughout North America that have shown environmental problems can't be looked at kind of as separate little issues because basically everything in an environment interacts with everything else. Some things are very much dependent on other things. Some things are not as closely related. But again, we have to look at the big picture, not just little separate pieces. And again, I think there's a bit of a challenge that again we as humans sometimes don't realize at this point, or we don't fully appreciate just how much the entire Earth is dependent on the other parts of the Earth, how much everything on this Earth interacts. Again, local interactions, regional interactions, but global interactions as well. And we have to kind of get that in our brains, that again, we can't just do something somewhere in the world and expect it not to cause problems, because so much of what we do can have a big impact on so many other parts of this planet. So reversing the ozone layer thinning definitely was started by banning the propellants. About a decade later, the Montreal Protocol basically stipulated that there needed to be a 50% reduction in CFC production by 1998, which gave it about 10 years. Again, larger scale, not just the U.S. who started the process. Companies who tended to be the biggest producers of different products, the CFCs basically, came up with substitutes that they could still use in the products they made to fill the niche of what the fluorocarbons did, and that basically these HFCs and HCFCs don't deplete the ozone. But then the other downside of it is that they are still potential greenhouse gases that could be as bad or maybe even worse than the carbon oxides. So you kind of solve one problem but potentially create another problem. Developing countries are phasing out CFC use, and the theory was they would have phased it out by 2005. And again, while that's mostly the case, there are still chlorinated fluorocarbons being used in the world, but again, fortunately, they're have mostly phased out now. And those other chemicals that replace the CFCs are going to be phased out within the next 15 or so years. And that means obviously that we're looking at other chemicals to replace those, and hopefully those won't have another different or worse impact than the ones that it replaced. So then the third issue that kind of all relates to these previous two is acid deposition. So basically this is another type of air pollution that includes chemicals like the sulfuric acids and nitric acids that are created partially down here on the surface of the earth, and when they get up in the atmosphere, combine with other elements in the atmosphere to create acids. We've observed that this has been occurring since the Industrial Revolution, because that's when we started burning fossil fuels to do our work for us. Acid rain was actually coined as a term back in the 1870s. Long time ago, again, we knew about this as a problem, but we valued the benefits of burning fossil fuels more than the potential, and at that point still not really very well understood, negatives that could be caused by acid precipitation. But there's no doubt that this is another very serious threat to the environment. In the U.S. alone, the annual damage from acid precipitation is predicted to be around 10 billion. In other populous countries like China, it's estimated that the acid precipitation affects about 40% of the country. So about 40% of the lakes, of the forests in China are negatively impacted by acid precipitation. So acid precipitation is created primarily when we burn coal, and coal is heavy in sulfur compounds, and then also when we burn fossil fuels under heat and pressure, as we do in our automobiles. These pollutants are carried by the wind. They get up in the atmosphere where they react with the water in the atmosphere to produce sulfuric and nitric acids. So you have the sulfur up in the atmosphere that mixes with the water vapor to create H2SO4, sulfuric acid. And then these acids come back to the earth either mixed with rain or any other type of precipitation, and even just back as dry particles. So this acidic particle is just as bad as if it gets mixed with water. It comes back as a type of precipitation. Now, again, something that most people don't realize is every time it rains on this planet, even long before we ever burnt coal, our precipitation is slightly acidic. It's actually called carbonic acid. It's got a little bit of acidity to it. And it's that acidity, that little bit of acidity, that basically created the caves that we have under the surface of the earth. What are caves? What are the types of rocks that are usually associated with caves? Marble, for example, limestone. Those are fairly soft rocks, and that carbonic acid that's in our rain normally is just acidic enough that as it leaches into the ground and moves, it can and did slowly erode away the limestone and marble to create the caves we have. So that slightly acidic precipitation does wear away rock. Now you make it a little more acidic by making sulfuric or nitric acid, and now you have the potential to damage plants, to possibly even kill plants that are a little more susceptible. Acid typically corrodes metals. How much of our society is made out of metal? External structures on buildings, bridges. And then we also look at so much of our artwork around the world. What are a lot of the statues that we see in Europe made out of? Things like marble, the rock stone faces on the outside of buildings. A lot of times those are marble or limestone. So we have so many of these cultural things worldwide, statues. We have so much infrastructure that we depend on that's made out of metal, that this acid precipitation is causing damage. And again, as that continues to corrode, we have to maintain these bridges, we have to fix them when they get so unsafe. And there's a money value to that. Obviously, we can pay to fix those, even though, again, that's going to cost each of us more money. But what happens when a statue that's from one of the well-known artists from hundreds of years ago, when that just starts losing its features and becomes just kind of a blob? You can't replace the cultural value that art provides to us. So again, when you start throwing all these things together, you're stressing out the environment by acidifying it, by causing more UV radiation to reach it, by the effects of the climate change, making the climate hotter, colder, warmer, drier, wetter, whatever. And you're causing these multiple stresses to the environment. And again, the more that the environment has to try and rebound from, the harder and harder it's going to be. And again, even if we stop burning coal in this country, which we've trended towards, we still burn coal, and we burn quote-unquote cleaner coal, and we've got more technology to scrub the coal. That still doesn't mean that we don't see the effects of precipitation, acid precipitation. It's kind of this constant downwind effect. Which way does the jet stream on the earth flow? It kind of flows clockwise, right? So any acid precipitation we generate on the east coast of the United States by burning coal, it goes across the ocean and lands in Europe. All of the acid precipitation that Europe generates goes across the continent and lands in China. All of the acid precipitation that China generates lands on the west coast, primarily in North America. It's up in Canada. So it's this worldwide exchange of the same problem. So again, it doesn't matter how much we in the United States don't do these things that are not helping the environment until everyone on the planet starts doing it as well. That's the only way we're going to solve the problem. So these acidic chemicals and gases affect locations that are nowhere near where they're created. And that's why it makes regulating them so difficult. Again, the US and Canada came to an agreement in 1991 to reduce acid deposition by as much as 35% in some areas. But again, a lot of the damage is already done. And again, that's only us in Canada. That doesn't stop what China does, and it doesn't stop what the rest of Europe does. There are a lot of streams up in the Northeast that are so acidic, even though for a couple decades now we've really tried to limit the amount of acid precipitation. Trees in Germany's Black Forest are dead and dying from the acid precipitation. So again, until we switch to an alternative cleaner fuel or find a way to remove all of the sulfur emissions from coal, we're not going to get rid of this problem. Remember way back I said that even though we and other developed countries have become less dependent on coal, a lot of other countries, especially those less developed countries, are becoming more and more reliant on coal because it's the least expensive resource and it's what they can afford. So again, it's great that we're getting away from it, and we should, because there are better options out there. But if China and India continue to develop and grow, and they continue to use more and more and more coal, how much worse is the problem going to get before we can start really fixing it worldwide? The case study talks about the international implications of climate change. Again, we're looking at social impacts, economic impacts, lots of different political factors that all complicate the efforts of us truly becoming dependent on renewable resources and not the non-renewable. We know that per capita emissions are higher in developed countries, like the United States, as indicated by the graph. You can see that we've done a slight improvement over the last 20 years. But the developing countries, like China, have more than doubled their emissions. India more than doubled its emissions, even though countries that are developed, like Japan, still have a net increase in their carbon emissions, and countries like France still have a net increase in their carbon emissions. So even though we've reduced them dramatically in certain places, there's still so much challenge ahead of us because, again, India and China want to move through the development phase. And to do that, they believe they need to use fossil fuels. And more importantly than that, they need to use the least expensive fossil fuels like coal. So again, even though per capita we produce a lot of emissions in these countries, imagine how much worse it's going to get in China and India as they continue to use more and more and more emission, create more emissions over time.